All right, so Tuva, are you accepting the folks in a meeting? All right. Hello, everyone. Welcome to our VFS webinar with NRC. Just going to wait a few more seconds before starting as we're admitting people. All right, so let's just get started. So hello everyone, my name is Chantal Boucher. I'm the VP for Americas for the Vertical Flight Society, and I'd like to introduce you to our VFS webinar, the Recent Vertical Lift Research at NRC. With that, I'm just going to introduce here our new officers. So as we like to always bring new ideas, we want to refresh the team as well and the officers. So we just elected 4 new officers very recently. So I'd like to welcome Tuva for his first webinar here. Tuva is now our chapter president. Tuva is also a program manager here at Bell for the commercial development program. And we have Wesley Reed from DART Aerospace, our vice president of the chapter. We also welcome Edith Richard, who's now our officer treasurer, and Martin Landry for our membership director. So you can see here on the slides, the other officers remain in position, and I'll still be around, of course, as the VP for Americas. So with that, I'll leave it up to Tuva to continue on the introduction.
Thank you, Chantal. Much appreciated. Hello, everyone. Thank you for joining us today. So my name is Tuva. As Chantal mentioned, I am the new president of the Ottawa-Montreal VFS chapter. And I'm also a program manager for development programs here at Bell. Before we get started, I just wanted to talk a little bit about the Vertical Flight Society itself and our mission. So Chantal, if you can go to the next slide. So the Vertical Flight Society was founded in 1943 as the American Helicopter Society, and it's the world's only international technical society for engineers, scientists, and others working to advance vertical flight technology. This particular conference is brought to you by the Ottawa-Montreal chapter of the VFS. And our mission really revolves around 3 pillars. So first, it's to increase the interest in vertical flight across Canada for both professionals and students. 2, it's to create a platform to facilitate networking and collaboration in vertical flight, in the vertical flight industry in Canada. And 3, it's to provide learning opportunities through exclusive conferences like the one you're participating in today. I invite you all to join us if you haven't already, and please do reach out if you want to be more involved in the community. Now, for today's main event, we have the opportunity to hear from the experts at the NRC on their latest developments. I'm very excited to introduce our distinguished speakers. Firstly, we have Mr. Duff Gowanlock, a research flight test engineer at the Flight Research Laboratory of the NRC. He is the technical lead for the Flight Autonomy Thrusts of Integrated Mobility program and is the project manager for the Canadian Vertical Lift Autonomy project, a 5-year, $10 million project demonstrating kit-based flight autonomy on the NRC Bell 412 Advanced Researched Aircraft. Next, we have Dr. Andrew Law, a Research Council Officer in the Aerospace Human Factors Group at the NRC Flight Research Laboratory. He holds a bachelor's and PhD degree in biomedical engineering and a master's in electrical engineering. His specific research focus is physiological signal processing and the neuroergonomic assessment of aircrew performance, stress, workload, and fatigue. Then we have Mr. Arthur Goebbels, a principal research officer at the Flight Research Laboratory of the NRC and a developer and facility manager for the 412 Advanced Research Aircraft, a unique $20 million national facility. His specialization is in helicopter control and handling qualities, and his research predominantly involves conducting flight test experiments using NRC's fly-by-wire helicopters. The current focus of his research involves designing and testing flight control algorithms for autonomous helicopters. And finally, Dr. Azzedine Dadouche is a senior research officer at the NRC. His main research interests are topics related to rotor bearing and sealing systems for gas turbines, as well as air-to-air collisions. The latter represents his current core research development topic at the NRC, including drone and bird impact of aircraft and rotorcraft systems. Now I'm going to hand it over to the speakers, but before I do, I just want to say we're going to take questions at the end. Feel free to type your questions in the chat box, and Chantal will be seeing them and asking them at the end of the session. And please enjoy the session. I pass it over back to Chantal and over to Duff.
All right, thank you, Tuva. So let's rock and roll. Duff, it's all yours.
Sounds good. Thanks, Chantal. Thanks for the intro, Tuva. It's a pleasure to be able to speak today to actually quite a large audience. It's greatly appreciated. My name is Duff Gowanlock. I'm project manager for the Canadian Vertical Lift Autonomy Demonstration Project at the NRC. And if I could just get the next slide. So over the next few minutes, I'll talk just briefly, just introduce the NRC briefly and the Integrated Aerial Mobility Research Program, which is where most of our vertical lift, but not all of our vertical lift research sort of resides. And then I'll take just a couple of minutes to talk about the Autonomy Demonstration Project, and then I'll turn it over to Bill, then Andrew, then Azzedine to step through their presentations, and hopefully gives everybody a bit of an overview of what we have going on. Obviously, we have dozens of research officers working in all sorts of domains around in aviation and vertical lift, and so this is just a few examples. And we definitely appreciate the opportunity to speak today, and certainly welcome any questions in this session or afterwards. So big picture, for those that don't know about the NRC, we're Canada's largest federal R&D organization, around 3,700 scientists, engineers, and technicians. Actually, next slide, please, slide 7, please. We span across the country geographically. Our prime role is to support business innovation, advance scientific knowledge, and support government in the development of policy solutions. Technology areas right across the board, from astrophysics, medical devices, human health therapeutics, digital technologies, etc., all the way into to aerospace, which we'll talk about today. And so within aerospace, we have the Aerospace Research Centre, where all of us presenting today work at. And we're split across 5 different laboratories, as you can see on the top row of the slide here, sort of spanning the gamut of technologies within the aerospace ecosystem. So today you have representatives of the Flight Research Lab and the Gas Turbine Lab. But obviously we have research going on across all the others presented here. And so the labs represent the where we sort of coalesce our competencies, the brilliant folks that are our research officers, as well as our facilities like the Bell 412 Advanced Systems Research Aircraft. Cutting across those, we have a number of research programs that sort of focus research activities across all those labs, and those are listed at the bottom. And we'll talk today in the next couple slides on the Integrated Aerial Mobility Program specifically, but we do have a lot of other diverse research areas, and are always happy to talk and engage on those. Next slide, please. So the Integrated Aerial Mobility Program is essentially focused on creating, supporting the creation of, or the growth of the advanced air mobility ecosystem within Canada, looking at increasing the supply chain, supporting the regulatory framework, and advancing niche technologies, all to help improve the ecosystem overall in Canada. Next slide, please. And so to do that, we've basically broken down the program into 2 innovation domains. I'll talk on this slide just for a couple of minutes, and then we have one more slide to help express all this. But we have the vehicle domain and then the operational domain. And then we break that down into master projects. And so on the integrated design side of things, we're looking at technologies around VTOL propulsor noise, VTOL cabin noise, And on the airworthiness and crashworthy structures dimension, we're looking at UAM structure and safety for crashworthiness considerations, simulations to optimize novel configurations for vehicle performance, and investigating low-cost structures for the broad VTOL applications. The other master project, operating environment, is looking at testing and modeling simulations around VTOL and eVTOL operations in adverse conditions, icing, rain, urban airflow. We also have research investigating small eVTOL air-to-air, air-to-ground collisions. We'll hear a little bit more about that today from Azadine. And this master project also looks at developing operator guidance and certification tools for operations in urban environments, which is more oriented towards eVTOL all the way up to urban air mobility. Next slide, please. The other aspect, the other innovation domain within the research program is focused around operations. And so flight autonomy, which is the master project that I lead, we're looking at developing and publicly demonstrating safe and effective autonomous flight system algorithms. We're also looking at detect and avoid flight test technology development and other test technique developments supporting autonomy, flight autonomous systems. Also looking at creating validation and benchmarking techniques for different levels of automation. All of that supporting the development of regulatory guidance, standards, and information for Transport Canada, as well as for defense applications through the Directorate of Technical Airworthiness and Engineering Support, who are the military regulators, of course. And then finally, we're also very interested in developing measures to assess trust in automation as part of all of this work, both for crew and passengers, but also for the general public. And then finally, the other master project, the fourth master project we have is integrated aerial services. And this master project is looking at developing aerial robotics technology for inspection and maintenance of elevated structures, as well as for security applications. This is also where we sort of house or contain our counter-drone and traffic management research areas, including RPAS traffic management, so integrating eVTOLs into the NAS, the National Airspace System. And also we have a lot of work in this master project around remote sensing, so the advanced applications of sensor systems, as well as analytics development for applying sensors to eVTOL. And next slide, please, Chantal. And so I mentioned a couple of times through the presentation, and certainly one of the main roles of NRC is to inform regulation development and policy development. And so within the program, we have a very tight collaboration, both with the military regulator, but especially with Transport Canada's RPAS task force. And so our research and development program under IM is very tightly linked to the development activities that Transport Canada is focusing on. And this slide here is a quick summary. I won't go through the details of it, but certainly has been presented in many different forums, and would be happy to answer any questions that may come up. So next slide, please. So with the sort of the high-level overview of NRC and the Integrated Air Mobility Program step through, I did just want to spend a couple minutes on our large program, our project around vertical lift autonomy demonstration. So I could talk for hours about the project. It's big and diverse. So I'm just going to take a couple minutes. I'll wrap up with a video, which is a good way to stop things, and then I'll turn it over to my esteemed colleagues to talk about their areas of research as well. So CVLAD, or the Canadian Vertical Lift Autonomy Demonstration Project, its objective is to demonstrate kit-based technology for advanced autonomous flight systems on both the Bell 412 and ultimately to evolve that technology for demonstration on board an RCAF Chinook. Our main focuses are around crew workload, hopefully reducing crew workload with the application of autonomy, as well as demonstrating improvements in operational capability and life extension, and helping develop the technology up to TRL-7. We have industry collaboration, and so that helps us link our demonstrations to a viable production path. And ultimately, all this work helps culminate in a strategic autonomy capability within Canada, and also helps enable the development of regulation. Next slide, please. So this is where I can really get down into the weeds quickly, and I'll try to hit the very high wave tops. So this demonstration project isn't looking at developing sensors per se, or computers or displays. It's more about the algorithms and architectures around autonomy. And so you can see a few pictures here and the words on the slide. I mean, our focus is really on architectures, looking at different architectures. And in the next slide, I'll talk about that for a minute. We're looking at technologies, algorithms around perception and generating a world around the autonomous flight vehicle, and then interpreting that world. So what are obstacles, what aren't obstacles, what are airborne threats, what aren't, and then of course developing trajectories or paths around those obstacles to achieve the pilot's mission objectives overall. Embedded in that is how do you manage missions, and how do you enact supervisory capabilities within the autonomy, and how are decisions made, and all that sort of thing. Of course, we're very interested in the integration with the flight control system, and what flight control laws are appropriate for autonomous applications, especially when you have supervised autonomy where the human may need to enter into the loop at appropriate points within the process. We're very interested in displays, and particularly the queuing, not the physical displays, but the information that are presented to the pilot, so the cues and how the environment around the aircraft are presented to the pilot. All of this involves a great deal of simulation, so we're investing in a lot of simulation capability within the lab to help support that development. And then finally, of course, testing and demonstrating the technology, developing test techniques, and ultimately helping provide that information to the community, to the ecosystem, and to the regulator. Next slide, please. So CVLAD, we have sort of three primary architectures that we talk about. And so the first two, the first one is sort of an evolutionary and an initial development capability, and we're actively working in right now, which we call the Peregrine Architecture. And so this architecture is developed in collaboration with a system from Near Earth Autonomy out of Pittsburgh. And it provides a low-range LiDAR landing zone evaluation capability that we're integrating into our world generation interpretation algorithms, and then around which we're providing trajectory planning, pilot queuing, and integrating with controls. And so this is sort of getting us going in the crawl, walk, run phase of things. And then from there, we build into a much more robust algorithm, which is sort of the strategic autonomy capability for NRC and for Canada, where we have a variety of different perception modalities, that we have then a variety of different techniques to develop a world scene, and then permit implementation of a number of different planners for trajectory planning, a more robust queuing system to the pilot, and then integrating that into controls for demonstration. And based upon that architecture, which is modular, then we can support integration with industry collaborators. So we can take industry autonomy cores or algorithm elements, integrate them together to achieve development, testing, and demonstration, depending on the nature of the collaboration, which is the case of how we get from developing technology on the 412 ultimately into the Chinook in one specific collaboration that we have along that industry architecture theme. Next slide, please. So ultimately, obviously, there's a lot of detail that I'm skipping over. Would welcome questions, but I didn't want to take too much time. I want to make sure you give time for my colleagues. So I mentioned we're starting off with this Peregrine architecture, where we have a LiDAR-based landing zone detection capability and safe landing zone algorithm that gives us a point amongst obstacles where it is safe to land. And so this is the system that we're actively flying and demonstrating at the moment. As we go through the crawl, walk, run phase, where we start with simulation of the capability, and then we go to open loop testing, where we have the system providing guidance to a pilot who then follows that guidance to make sure that it all works effectively and properly. It also helps us develop our test techniques. Then we ultimately step into closed loop flight testing, where we then feed those guidance signals into the flight control computer, and then the pilot who was in the loop now becomes out of the loop or on the loop and is in a supervisory role. We're currently in the open loop flight testing phase of that. And so we've been conducting a number of flight operations over the last several months, here at Ottawa at our Upland site, and so anybody that's familiar with the aerodrome would and where the lab is situated, you'd sort of see the picture on the right is a top-down view. The airport's in the bottom of the scene, and then we're flying around. In this case, a little mission flying around the EY Center, which is a convention center near the airport here, just doing a little circuit to land. And so that's we're currently in that open loop phase, proving out the system, and then very soon we'll be closing the loop on that, providing that guidance input into the flight control computer, and we expect in the very, well, not too distant future, very near future, to have that first full-scale autonomous flight in Canada to be able to demonstrate publicly. And so the next slide just provides a bit of a video of one of our recent flights, just to give a flavor of what we're doing. And so, yeah, Chantal, if you can press play on this. And so this video shows, and hopefully it comes through all right. Oh, I lost, oh, there we go. There we go. So this video shows just that little circuit around the convention center near the NRC. And so the bottom left picture is a cockpit forward picture. You can see our displays. The left display, probably not on my screen, the video quality is not awesome, thanks to the internet. Shows the pilot guidance being provided by the autonomous system. And on the right display, it's sort of a top-down navigation display to help with situational awareness. So we had a broad mission, like just a circuit programmed in here, and then that is our autonomous system is providing guidance to the pilot to fly. Not unlike an autopilot, it's very similar to that for that phase of flight. And then we come around, and now we're coming into the landing. You can see the wind tunnels complex off to the right on the top right image. Ahead of us in our low-speed test area, we have an open field. We've selected a 30-meter radius circle as our landing zone, and then populated it with a number of obstacles that the autonomous system is unaware of. And now the LiDAR system is scanning the landing zone as we come in to seek out the obstacles. And we should see some information up on the display. Hopefully that comes through. So we now, hopefully it's visible on your version. There's a display provided to the pilot that shows the landing zone coming into view as the system is scanning. And in the picture on the right, you can probably see some of the obstacles. They vary a variety of sizes. They're not very big obstacles. The maximum diameter of an obstacle is 40 inches. The system generates a safe landing zone algorithm, and so this is a still picture on the top left. Gives us color coding information. In the back, the engineers are looking at this information, obviously, to assess where is a safe landing point. The pilot itself gets a display of where the landing point is. It's a little home plate shaped image. And then he just, through the flight control system, command attitude hold, flight control mode in this case, steers the aircraft over to the desired landing point. And then ultimately, once we're over the landing point, in this case, we just descend to land. And so that's just a sample example of an open loop test that we're doing. You can see some of the obstacles come into view a little bit better on the top right and in the bottom left image there as we incrementally develop the technology. And as I said, the next step will be to take that guidance information and feed it into the flight control computer to then repeat that test and that demonstration in a full closed loop fashion. And then, of course, increase the degree of difficulty of those profiles. In this case, the demonstration I showed here was a pretty low degree of difficulty overall in terms of obstacles. But then, of course, as the capability increases, we'll increase that capability or that complexity. So yeah, that's a quick overview of sort of an example of one demonstration, and I did just want to touch on the regulatory theme. Of course, as part of all of this autonomous development work that we're doing under CVLAD, we have a tight collaboration and a standing working group formed with Transport Canada and DTAS, the military regulator, studying a number of factors around autonomous flight systems. You can see them listed here. We also have NASA and FAA participation in that as well to help glean the bits of knowledge that we can generate out of our development activities and help inform the development of regulations. So so that as autonomous flight systems are introduced into the market, the regulatory environment will be ready to accommodate and absorb it. And with that, I know it's a very quick and dirty overview, or a quick overview, I guess, to say, of the CDLAD system. I definitely would welcome questions at the end, and please feel free to reach out to me over email or text anytime if anybody wants to follow up or have any questions. But with that, I'll turn the floor over to, turn the mic back to Chantal and over to Bill.
Good day, everyone. My name's Bill Gubbles. I hope everyone can hear me. I'm going to just give you a brief overview of some of the activities that I'm involved in Rotorcraft flight simulation model fidelity improvement and assessment. This is a collaborative effort between NATO nations that we are involved in to develop improved rotorcraft simulation models. So next slide, please. So the NATO ABT 296 working group is our collaborative activity we have participants from government, academia, and industry, and representatives from a number of NATO nations are on the working group. Including Canada, US, UK, France, Italy, Germany, Netherlands, and Turkey. And we even have non-NATO Australia joining in as a partner nation. The objective of the work is to identify, refine, and document physics-based flight dynamics model updates or improvement methods that we can use and find the best practices and suitability of each method. As well, once we've determined how to update the different simulation models to improve them, we need to have different methods to assess and refine those models so that we know how good the models are. And we also want to produce a set of common metrics that we can use across the participating nations so that when we are talking about how good our models are, we're all talking about the same, we're speaking the same language and talking about the same things. So the basic idea is using the knowledge gained from flight test data, you can take your original baseline model and using the methods that we've determined as part of our group, we can update that helicopter model to represent one that has an improved level of fidelity. Next slide, please. So one of the outputs of this group is a report that describes in detail what these model fidelity improvement methods are and how to apply them. The report also provides a kind of a level of effort indication. So how difficult is it to apply these methods? Because some methods are quite simple and others are very complex. And actually, the methods, as I've outlined on this slide, are arranged from basically the simplest method up to the most complex and the one that takes the most amount of effort. So the first two methods, gain and time delay corrections for key responses and black box input-output filter corrections, these methods do not modify the baseline model at all. Instead, the corrections are applied to the external structure of the model, either as single input, single output gain and time delay corrections, or multi-input, multi-output correction filters. The next four methods modify the baseline model. So method 3, force and moment increments, basically you use a comparison between the stability and control derivatives as identified from flight test with those from the baseline model. And from that, you can derive force and moment increments or decrements that have to be added to the baseline model to improve the result. So method 4 is reduced order models and physics-based corrections. This improves the baseline model by adding physics-based model structures for higher order effects such as inflow dynamics, rotor wake interference, engine drivetrain dynamics, and actuator dynamics. The next method, simulator model parameter adjustment, aims at adjusting aeromechanical parameters. And those would be things like moments of inertia or hinge offsets through matching stability and control derivatives or through minimizing frequency domain errors. Method 6, parameter identification of key simulation constants. This is where we use system identification methods, either time domain or frequency domain methods, to directly determine different rotorcraft physical parameters that are part of the model. And these could be things like fuselage blade inertias or flapping and lagging hinge offsets. And you can use flight test data to determine these quantities and thereby update your physics-based model to a higher level of fidelity. And then finally, method 7 is a stitch simulation model from point ID models and trim data. In this case, we completely replace the model by stitching together a number of linear models at different anchor points. And then these linear models can either be identified from flight test data or they can also be derived through the numerical linearization of nonlinear simulations. So you can take a really complex nonlinear simulation, develop a stitched model that would allow you to run in real time for things like piloted simulation, because some of these nonlinear models are too complex and too intensive in terms of processing power to be able to run in a real-time sense. Next slide, please. So a primary question to be answered when applying a system identification for improving a simulation model is what validation criteria should be used to evaluate the model quality. How do you know that your model is any good? How do you know that you've improved it? So over the course of this NATO activity, the group has identified 7 methods to evaluate the quality of a model. The first method involves the concept of maximum unnoticeable added dynamics, also known as MUAD, or as well allowable error envelopes, which is a very similar method. They just have different criteria applied. And this is used for determining whether the math model is adequate and if the simulation facility is adequate to accomplish the proposed evaluations. So these are frequency-based frequency domain techniques where the error in frequency response between flight test and simulation is plotted against the allowable boundaries. So you can see on the right, the right figure at the top, that's kind of an example where the gain and phase error has been plotted and against the criteria. And these are this is the MUAD boundaries. The allowable error technique has different boundaries, but it's the same basic technique. The next method, which is a model flight data mismatch and integrated cost functions. This basically you use the cost function in either the frequency domain or time domain to assess the fidelity of the simulation model. So basically, you could take the errors, for example, from the MUAD plot that was just presented, and sort of distill that down into one number, and then you can compare those cost function values as a form of fidelity assessment. The ValCrit T and ValCrit F validation criteria were developed to assess the simulation model fidelity in both the time domain and frequency domains. And these were developed in a Garter working group in Europe to detect statistically the difference between simulation model and flight test data. And then the next method addresses the problem of motion queuing fidelity as part of simulator device acceptance. And then the simulation fidelity rating scale is a subjective scale that was developed out of the University of Liverpool and is being widely used these days as it's a subjective method that uses pilot evaluations to evaluate the fidelity of a simulation device for flight training. And then finally, the qualification test guide performance standards these are a standard criteria that is used by regulators for simulator qualification as a training device. Next slide, please. So we have methods to update our models. We have ways of assessing those updates to determine whether what we've done is an improvement. Finally, the sort of the third leg in the stool is how do you what data do you use to apply these methods? So we had a number of aircraft databases that we put together that we acquired from a number of different aircraft, and this was done to support the case studies that in the report are used to demonstrate the different methods and their effectiveness. So ideally, what you'd want to do is have multiple different aircraft configurations so that you would be able to test the methods on a variety of different cases. So, our goal was to find things like single main rotor helicopter, tandem rotor helicopter, coaxial rotor, fenestron equipped, or even a small quadcopter. And so we have all those types represented. We have a variety of different sizes, from a 3-pound quadcopter up to a 50,000-pound Chinook. And so we've covered kind of the gambit in sizes. And you can see a list of the aircraft on the right of the slide. We had, of course, the NRC's Bell 412. We had U.S. Army's UH-60. And then we had aircraft from Europe, including an EC-135, AW-139 and 109. And we also had the coaxial Sikorsky X2 technology demonstrator, which gave us a sort of yet another different rotor system to apply these methods to. Each database contains enough information to be able to support the modeling efforts, including weight and balance information, rotor characteristics, and as well as other configuration data, and then finally a summary of what flight test data was available and what form it took to be used for modeling. Next slide, please. So what's the result of the of this activity? It's mainly a report. So this is a large NATO report. It fully describes all the update methods, what fidelity assessment metrics were used and how to apply them, and as well the aircraft databases. And then the report includes as well several case studies or examples for each method, so that people can learn from the group and see how to apply these methods. And then next slide, please. And then finally, along with the report, we do have a lecture series scheduled. This lecture series is really intended for any practicing engineer or researcher who uses rotorcraft modeling and simulation for a variety of different things, including for flight control law, for design and development of aircraft, and for training. And I would invite anyone who is in this area of work who is interested to join the lecture series and maybe learn a little bit about the state of the art in aircraft, in helicopter model improvements and fidelity assessment. And so we have our European lecture series from early June 1 to 3, and our North American lecture series from June 8 to 10. And that concludes my presentation. Thank you all for listening.
All right, thank you, Bill. And let's turn it on now to Andrew Law.
All right, great, thank you. My name is Andrew Law. I work in the Aerospace Human Factors Group at NRC. And I really appreciate this opportunity to present a recent study we've done on helicopter pilot workload. Next slide. So the motivation for this work is to develop new methods for quantifying pilot workload in flight. Typical techniques include subjective ratings and task performance metrics, and some challenges we face are that subjective ratings are not time resolved, and each person has a different nonlinear stress performance curve that has hysteresis and time dependency. So we've been looking at other candidate metrics based on behavioral measures, peripheral physiological signals, and brain monitoring techniques. And in this presentation, I'm going to focus primarily on control activity, heart rate, and EEG parameters. Next slide. So for this particular study, we developed what we call a virtual target tracking task paradigm that can be flown in our Bell 205 fly-by-wire helicopter. The task involves two displays in the cockpit. The right display provides ownership referenced target position, velocity, acceleration using a modified BOSS symbology. And the landing point symbol serves as the target cue. The left-hand display provides Earth-referenced target information using X-plane, and we use two inline follow-me helicopters that serve as the target. For all trials, the target is moved laterally in a pseudo-random manner relative to the initial heading of the helicopter at 3 different levels of difficulty, which correspond to 3 different levels of target velocity. And we've applied a randomization in time and amplitude inversion to try to minimize learning effects across trials. In this particular task, we instructed the pilots that the desired performance was to always maintain a tracking error less than 10 feet over the 2-minute trial, and adequate performance was to maintain tracking error under 20 feet. Next slide. So for this particular study, we configured the fly-by-wire system on the 205 with attitude command, attitude hold, yaw and heave axes under automated control. The image on the right shows the position of the helicopter relative to a starting hover position, which is that vertical line, for low, medium, and high difficulty trials. So the position of the helicopter you see in the image is 60 seconds into the trial. For the low difficulty condition, the target is barely moving, so the aircraft doesn't really move very much relative to starting position. But for the high difficulty trials, the position is varying plus or minus 120 to 150 feet laterally in both directions. Next slide. So we did these experiments with 2 test pilots, 2 NRC test pilots. They alternated as the safety pilot in the left-hand seat and the evaluation pilot on the right side. The evaluation pilot wore the physiological sensors for heart rate and for EEG. The study took 2 weeks for data collection, and each pilot served as the evaluation pilot for 3 flights. In addition to the physiological measures, we did record all the aircraft state information, target state information, control activity. We did record eye tracking with Tobii Pro glasses, but we had some challenges with ambient light saturation of the eye tracking sensors. So that's not included in this presentation. And for subjective ratings, we use Cooper-Harper handling quality rating scale. The first flight for which each pilot served as evaluation pilot, we treated that as a task familiarization flight. So the results that I'm going to show are for flights 2 and 3 per pilot. Next slide. To look at tracking performance in this task, we computed the root mean squared difference between target and aircraft position over the full 120-second trial. On the left-hand side, I'm showing an example of a medium difficulty trial where the lateral and longitudinal position of the target is shown as a dotted line, and the actual aircraft position is shown as a solid line. On the right, we have the RMS errors during flights 2 and 3 for both pilots as a function of task difficulty, and we found that the RMS tracking error was proportional to task difficulty as we expected. Next slide. For subjective ratings, we decided to use the Cooper-Harper handling quality rating scale. For those that are not familiar, the pilot has to evaluate performance relative to desired and adequate criteria, and then within those bounds, identify the level of pilot compensation required to achieve either desired, adequate, or to attempt to achieve adequate if adequate is not attained. In this particular case, we found that for the low and medium task difficulty, the pilots were able to achieve desired performance, which was maintaining a distance of less than 10 feet from the moving target. But the compensation ranged from minimal to moderate, going from low to medium difficulty. In the high difficulty trials, the fastest velocity trials, the pilots were able to achieve adequate performance, and they usually reported extensive compensation required in that case. Next slide. We then looked at control activity, and we used a metric that has been used previously by our group and other groups internationally. It's called the Dynamic Interface Modeling and Simulation System Product Metric. All it is the product of cyclic control reversals and cyclic standard deviations in a 3-second moving window. So we applied that metric for the lateral axis of the cyclic and longitudinal axis of the cyclic separately, and then summed together and averaged over the 120-second trial. As you'll see in the right-hand side, the control activity metric was proportional task difficulty, similar to the tracking error in the HQRs. So these three analyses essentially confirm that the manipulation of pilot workload that we intended was successful. Go to the next slide, please. We then took a look at heart rate. Heart rate was measured from electrocardiograph signals recorded in flight. On the left-hand side, I'm showing an example trial where you see the lateral target velocity at the top, and then a lateral cyclic position, second row. Third row is an ECG recording. Bottom row are the interbeat intervals derived from ECG. And so from interbeat intervals, we can compute heart rate in different windows. We can do heart rate variability analysis. To keep it simple here, I'm just showing the average heart rate per trial. And we did have to do a normalization for each flight separately because there's non-stationaries across time. If you measure someone's heart rate on a Monday doing a task and you have them come in and do the same task on a Tuesday, there might be an offset in heart rate based on many factors that are outside of our experimental control. So we normalize the heart rates within each day and then combine the results. What you see on the right-hand side are a normalized heart rate as a function of task difficulty. And again, what we found is that there's a proportional relationship here as we saw with the other metrics. So there's a lot of redundancy between these different metrics, which is a good thing. Next slide. So then we looked at EEG. EEG is a very complex signal to understand. And the reason for that is the EEG signals are time varying, frequency varying, and spatially varying. And the signal to noise ratio is often very low. So when we go into a dynamic and very noisy environment like a helicopter cockpit in flight, a lot of these subtle differences in what you might pick up as a signal in a controlled laboratory environment are just in the noise when you go into the real world. So we tried to keep it as simple and straightforward as possible. What I'm showing in these tables are some workload and task engagement indices that were proposed about 20 years ago, and they are effective when looking at workload and engagement in a controlled laboratory environment. Each index is a different ratio between the amplitudes of different frequency oscillations. So for example, workload index is the ratio between frontal theta and parietal alpha. The engagement indices, the first one is beta over alpha plus theta. But I'd just like to draw your attention to the fact that in all four cases, alpha is in the denominator. So alpha rhythms, which are in the 8 to 13 hertz range, were found to be inversely proportional to workload and engagement in multiple tasks in a controlled laboratory environment. So we decided to focus on alpha, and our expectation was because of this inverse relationship between alpha and these different indices, that we would expect to see highest alpha amplitudes during the low difficulty task and lowest alpha amplitudes during the high difficulty task. But what we found was that alpha was highest during what we called the medium difficulty trials. And that's what's shown on the right-hand side. So this caused us to go back into our debriefing notes and look at pilot comments. And what was interesting is that during the low velocity trials, the motion of the target was very slow and at times difficult to differentiate from gust-induced shifts in the own ship position. And both pilots reported that a good cyclic trim position was really critical during those low velocity trials because very small, precise control inputs were required to avoid over-controlling and then overshooting that barely moving target. Conversely, for high velocity trials, the target was moving so fast that the pilot had to be in a high vigilance state to detect any early sign of a direction reversal in target motion. And if their attention lapsed at all, they would overshoot. So the medium velocity target trials were kind of this in-between task where the pilots they had to maintain attention, they had to be hands-on, they had to be active on the control. But the level of engagement and attention seemed to be less than when the target barely moved or when the target moved at a high rate. Next slide. So just to conclude briefly, what we found in this particular study was that control movements and changes in heart rate were proportional to target velocity tracking error and subjective ratings. EEG told a different story. And one of the comments from one of the pilots was that a medium velocity trial seemed like driving home from work without paying attention. And we all know what that feels like. We're kind of on autopilot. Eyes are open. We are making movements on the steering wheel, corrective action, but it doesn't require full max attention. And so that's what we think the EEG measures were telling us that was not apparent in any of the other metrics. Main takeaway here is that pilot workload is a multidimensional problem. And to really understand what's happening, we need different metrics that are sensitive to different dimensions within that space. Next slide. So where are we going from here? Obviously, what I've shown you today is a preliminary study with 2 pilots. We'd like to explore doing this with a larger sample to see if these results hold. The problem of vibration and electromagnetic interference in the helicopter is critical with EEG. And so we're working on adaptive filtering techniques to try to do a better job at extracting signal from noise. Calibration of these indices is also challenging. As I mentioned before, there's a lot of non-stationarity in any type of physiological signal. So how do you baseline your measurements, or how do you benchmark them? That's an area of study. And going back to one of the references I mentioned earlier, so in 1995, Alan Pope at NASA did this biocybernetic loop experiment in a controlled lab. And we'd like to move in that direction so that we can process the data in real time, and we can toggle either display information on off based on real-time inference of cognitive state, or change the control paradigm itself. So those are different areas of future direction. Next slide. And in conclusion, these are some of the references for those that are interested to our recent papers we presented at BFS. Others are more some of the background to our work. And I'm happy to address any questions either during the session or offline. With that, I'll hand it over to Azzedine. Thank you.
Thank you, Andrew. And it's all yours, Azzedine.
Yeah, hello, everyone. Thank you for coming to this presentation. My name is Azedin Dadouche, and I'm a research officer at the NRC Gas Turbine Lab. During those kind of maybe 10 minutes of talk, I'll be talking about drone impact testing that we have completed over the last 3 years here at the NRC. I'll just give a brief summary, and then, of course, I'll be open to answer any questions. So the objective of our series of projects we started about 3 years ago, as mentioned, are number one is to assess the damage severity that may result from drone impact on aircraft structure or windshield. This is number one. The other objective was to support regulators, because so far there is no kind of clear regulations about drone operations and zoning and or clear or zoning for drone operation. So this is to support the regulators such as Transport and Defense, such as DND or DRDC, with experimental data and damage analysis to create evidence-based rules for drone airspace usage. The last or the third objective of our investigation was to validate and fine-tune advanced FEA modeling and simulations so that we can assess the damage severity without the need to go for experiments. Next slide. Next slide. Yeah, so I'll first start by saying a few words about NRC expertise in terms of bird impact or bird injection for engines. So the NRC is one of those R&D centers throughout the world that support aircraft and engine manufacturers to certify their products against bird strikes. So the first windshield and aircraft structure bird impact was completed at the NRC back in 1965. This was before I was born. So there's a lot of people were doing that at the NRC. So we have a number of cannons that are available for usage, depending on the impact, depending on the projectile size and the speed you would like to to have the impact at. So we have cannons as small as 3.5 inches in diameter and up to 43.8 centimeters, which is 17.25 inches in diameter. So the two, the top and the middle pictures show the 6-inch cannon that we use mainly for bird impacts, and the bottom one is the biggest cannon that we have built in collaboration and partnership with Transport Canada and the RDC. So this is the drone cannon, or as we call the super cannon. And we have completed pilot testing on flat plates to verify to validate some simulations, as well as on aircraft segments of Part 23 and Part 25 categories. So next slide. In this presentation, can you click again, please, so that you can see the picture there? Thanks. Again, yeah, another one. Yeah, so I'll be talking about the Part 25 aircraft testing. So the objective also for this was to assess the damage severity on the aircraft systems, and also study the risk of collateral damage and also the risk of fire. So as you can see here, so we have selected kind of 3 main systems of the aircraft. So on the left picture, you see a wing of transport category aircraft. This is kind of a huge wing, and we had to slice into 3 portions so that we can have it into our test facility for impact testing. We have up, the right top side picture is an empennage of, it's a T-shaped empennage of transport category aircraft. And also we had to slice it into 3 main pieces. So 2 portions of the horizontal stabilizer and 1 central portion of the vertical stabilizer, and few portions of the horizontal stabilizer. And the bottom sketch shows a structure of a windshield that we have also tested. And as you can see, the windshield for this aircraft is composed of 3 main layers. So you have the non-structural protective outer glass pane, which is the external one, and then you have the medium structural vinyl interlayer, and then you have the structural inner glass pane. So I'll be speaking about few tests that we have done on this segment. Next slide. Okay, so the top. So this is a setup for the wing leading edge testing, and of course for the wings you have the slots, and depending on your flight configuration or your altitude, you may have the slots fully deployed or fully retracted. So the objective here was to test or to have impact testing done on the wing leading edge at altitude up to or under 10,000 RPM, under 10,000 feet, which is about 3 kilometers. And we know that the maximum speed that an aircraft can operate at is about 250 knots. And we have also done other tests at 140 knots, which represents kind of an approach speed of such an aircraft. So the speeds here, as you can see in this table, 140 and 250. So the 140 we deployed because it's kind of its approach, and this speed represents the speed of the aircraft as well as the drone. So this is kind of the addition of two speeds. So the top left picture shows the test configuration for a wing in with fully deployed slats. And the bottom right picture shows a portion of the wing with a fully retracted slat, and this test was done at 250 knots, whereas the other one was done at 140 knots. The other picture showed drone in its sabo, ready to be launched against the test articles. Next slide. Okay, so here I'm showing a picture. I'm showing a video of drone impact at 250 knots on the wing segment. The wing here, yeah. So the wing here is retracted, fully retracted. So this represents kind of impact under 10,000 feet. Yes, go ahead. Oh, you don't see the video. We haven't seen it. There you go.
Yeah, it sounds like I may have just a little small technical issue to play the video here.
Not moving.
Do you want to keep going, maybe?
Yeah, sure. Yeah. Okay. So yeah. So next. So here you will see pictures of the resulting impact. And as you can see, there is kind of significant damage to the slat here, as you can see. It's not very severe, so we didn't get to the wing leading edge itself. So it was just the slight slat damage. And after the test, we tried to deploy the slat, for example, and it was impossible. The slat was stuck on the wing, which may be kind of a little of an issue if the pilot tries to land, as the slat cannot be deployed. A picture at the very bottom, you can see the battery. It was kind of it was severely damaged, and it was burning. Of course, few feet beyond the test article. Next slide.
Let's just try again.
Yeah. Anyway, so it doesn't work for this video. So let's see. This is another setup for this is for the empennage testing. The top left picture shows setup for the one segment of the empennage, horizontal stabilizer, and where the test target is located, as you can see, kind of a round circle between the leading edge rib number 20 and number 21. The right-hand side picture shows the vertical stabilizer setup. The vertical stabilizer in that case was tested in upside down configuration, because this was kind of the best way to have it set up properly. And there were also some other safety reasons that forced us to do it that way. Next slide. Another test was done on the same on the other segment of the horizontal stabilizer, and this was done. We wanted to compare the impact or the damage severity between a bird and a drone. So the bird that we have used in this test was had the same weight of the drone, which was about 2.6 pounds. And as the cannon also, so we have replicated the same strapping mechanism that was used on the drone, so that we replicate the same boundary conditions. For that test, we have used a different cannon. We have used a 6-inch cannon because of the size of the bird, as you can see on the right-hand side pictures. Next slide.
Okay, hopefully this video is going to work this time.
Hopefully, yes. So the left-hand one, please. Okay, voila. So it works. So drone on target. So this was done with a fully charged battery, and of course, you know, the leading edge was completely destroyed, and a few motors with the main battery, the main body of the drone with the battery landed inside. What happened? The problem is that the battery, you know, overheated and ignited, and there was a lot of smoke in the area, and we had to take that segment outside. A lot of damage to the leading edge ribs, as well as to the front spar. Next slide. Next video. This is a comparison with the bird. And to our surprise, the bird made it through as well. And as of course, the bird needed to be kind of, you know, protected in a bag so that we reduce the mess. And the bird made it through the leading edge. The damage was not as severe as the one with the drone, but still, I mean, there was damage to the leading edge, as you can see, as well as damage to the front spar. Next slide. This is another test we have done on a windshield, again for Part 25 transport category aircraft. And as you can see on the left-hand side picture, you can see the window of the windshield was supported on a special frame while respecting the layback angles of the windshield. And the top right hand side picture shows kind of the cannon as well as the cameras. And I don't have a video for that test, but as you can see, I have pictures that were extracted from the video where the impact at 250 knots caused kind of significant cloud of glass fragments as a result of the impact. And this generated glass fragments were, you know, at the outside as well as the inside part of the test article. Next slide. A lot of details. So we have published reports on this test, and you can find them under those links. That they are open to the public. If you have questions, please let me know. Go next slide. So our future. So of course we have done also a lot of testing on Part 23 aircrafts. We have just finished the test, and the report is being written as well. And we may be public public for people maybe in few months. Future studies, or we are now working on a different project for Part 25 transport category aircraft, where we would like to study the impact on the windshield with its while mounted on its cockpit, because the test that we have done on that windshield made us worry about what would happen to the pilots. I would like to have a test with the full cockpit and have a witness plate with a lot of instruments to study the effect on the pilots as well as the aircraft. The other part we are looking at is do some testing on rotorcrafts, mainly the swash plates assembly as well as the windshield mounted in its original cockpit, as you can see in this picture here. Thank you very much, and I think I went a little beyond my allocated time. Thanks, and I'm open for any question.
Yeah, let me try to see if I can bring up your video that we didn't see.
Oh yeah, it's good. So the drone was completely destroyed as a result of the impact, shattered all over the place. And this drone was used. Why this drone was selected for the testing? The reason is this is kind of the most popular drone which is being purchased by our Canadian fellows. So we wanted to, you know, to use the drone that's in service. Thanks.
All right.
Yeah.
So with that, we normally wanted to have a period of question, but I understand that we passed a little bit of our time. It's 12:40. There's been actually a lot of questions asked on the chat. So I feel really bad about all of these questions being unanswered. Duff, is there a way that they can ask your team the question, this question, to reach out to you? You did mention your email at the beginning.
Yeah, definitely. If we can get sort of a transcript of the chat, I can share that amongst the team, and I'm sure we can provide a little summary response back. And then perhaps it could be posted with the video online so people could have a look at it. Otherwise, I don't know that we'd have the ability to go back one-to-one, but unless people reached out directly to me, and then I can, of course, put them in touch with the right researchers.
Sure. So let me see if I can get you the emails of the people who asked the questions, and with along with the question. I guess one question that is quite easy to answer. How can we join the lecture series? That's a question for you, Bill.
Yeah. So I have a lecture series flyer that has all the information in it. I can email that to whoever would like to join that lecture series. What do you think, Chantal? Should I just email it to you and then you can forward it on, or do you want to give them my email and they can contact me? Either works for me.
Okay, so I'll let you know of the person who asked the question. All right. So with that, thank you much, Duff, Bill, Andrew, Azadine. That was great. A lot of interest during the session. At some point, we were over 80 people, so obviously a lot of interest from the crowd. We're gonna try to make this this presentation also available for replay for those of you who may have missed some portion of it. And with that, thank you all. And I think, Duff, we're going to be able to see you during Forum 77.
Yeah, exactly. I'm part of the Civil R&D panel. Yeah, looking forward to it.
All right. Thank you so much. Thank you all for participating, and see you for the next one.
Thank you. Bye.
Thank you.
Thanks.
Thank you.